This talk is sponsored by the Central Virginia node of the Commonwealth Cyber Initiative, and CCI is a state program establishing Virginia as a global center of excellence in cybersecurity research through supporting research, workforce development, and innovation at the intersection between cybersecurity, autonomous systems, and intelligence. And every year, CCI and CVN sponsor research and experiential learning projects, and today's speaker is the recipient of that funding. So today we have Dr. Nastassja Lewinski. She is an associate professor of chemical and life science engineering at Virginia Commonwealth University. She has a PhD in bioengineering and a BS in chemical engineering from Rice University. And she's a distinguished researcher specializing in nanomaterial toxicity, nanomedicine, and nanoinformatics. Her impactful career has been recognized with prestigious awards, including the AICHE, I don't know if I'm saying that right, 35 Under 35 Award in 2017, the Leonard's Nested Research Projects Award in 2014, the Whitaker International Scholar Award in 2011, the NSF Graduate Research Fellowship in 2008, and the Barry Goldwater Scholarship in 2005. Today, she's going to share insights into the Cybersecurity Initiative in bioprinting, exploring the security challenges in bioprinting technologies, specifically investigating vulnerabilities in extrusion-based bioprinters to cyberattacks. Enjoy the session of our spring speaker series and be sure to save for the Q&A session afterward.
Thank you for that kind introduction. Let me share my screen so I have some slides to share with you today. I appreciate you all attending this seminar on Valentine's Day. And I would like to thank Erdem Topsicle and the organizers of the Central Virginia Node seminar series, as well as the CCI community, for this opportunity today to share with you some of my group's research that's being conducted in collaboration with Dr. Irfan Ahmed's group here at VCU on the cybersecurity of bioprinting. So if you'll have noted from the introduction, I'm in the Chemical and Life Science Engineering Department. For some of you, this talk may be cyber light. So before we get into the core focus of this talk, let me introduce a bit about my lab and how we got here. And so my research group studies the biological interactions with and responses to nanoparticles and particles and mixtures using in vitro models. And so we've contributed to areas, as mentioned, nanoinformatics, nanomedicine, nanotoxicology. And recently we started exploring, can we use bioprinting to assist in making advanced 3D in vitro models? And so the focus of this talk is going to be around bioprinting work. So I'm not sure how many of you are familiar with bioprinting. So for those of you that are not, bioprinting involves creating living tissues with a specialized 3D printer. And so that's what we mean when we say a bioprinter. So there's different types of bioprinters, 4 of which are shown on this slide. So you have extrusion-based bioprinting, stereolithography, digital light processing, and 2-photon polymerization. Notice that several of these involve light to polymerize and build each tissue layer by layer. We chose to focus on extrusion-based bioprinting because it is arguably the most widely used bioprinting approach due to the availability of low-cost commercial bioprinters. And with extrusion-based bioprinting, unlike the light-based polymerization and building of the tissue layer by layer, here the bioink is physically extruded through the nozzle of the printer and then built layer by layer. To go into the bioprinting workflow in more detail, if you're thinking about bioprinting in the ultimate goal of regenerative medicine, then you could imagine that a patient that may need a tissue transplant could be have that organ imaged using different 3D imaging modalities, such as magnetic resonance imaging or MRI, or computed tomography or CT. And this 3D imaging then would allow the generation of a 3D model of the tissue to be printed. This then 3D model can be converted using slicing software to generate G-code. And so G-code is the machine instructions for the bioprinter, which you can think of as a type of CNC machine, to then be able to move and create those the features, the geometry layer by layer. And in addition to needing the G code, you also need to prepare the bioink that I mentioned earlier. And so there's different definitions of what a bioink consists of. This still needs to be standardized in the community, but what we count as a bioink is cells that are encapsulated in a hydrogel. And so you would prepare then that bioink and load it into the bioprinter. So here is so you load the bioink into the bioprinter, and then with the G-code instructions, it will generate your 3D printed construct. Now, depending on the chosen bioink formulation, there may be some post-production processes, such as there may be a need for physical cross-linking, or common also is UV cross-linking to then set the structure. And so in addition to maintaining the shape integrity throughout the process, another critical parameter that needs to be taken into consideration is maintaining cell viability throughout the process. And so a lot of times folks wonder, how is bioprinting different from just 3D printing? From a machine perspective, you could argue it's very similar. However, a fundamental difference between bioprinting and 3D printing is that bioprinting involves living cells. And so this is an added variable that needs to be taken into consideration. And so to better visualize the process, I have a video to show you here, which is a short demonstration of the use of the bioprinter in my lab.
Hi, I'm Mary, and I'm an undergraduate researcher in Dr. Lewinski's lab. And today I want to give you a short overview on our research on additive manufacturing or bioprinting of living tissue. So in our lab, we use extrusion-based bioprinting using bioinks that we custom formulate. Using CAD, we've designed several constructions that we use to help us assess several parameters such as traceability and cell viability. You can see that the construct is being printed multiple times, and each time the print speed or temperature, for example, is changed slightly to determine the threshold where the printability begins to fit. Currently, our lab is working on quantifying these quality control parameters so we can specify the normal conditions of the bioprinter so that we can detect sabotage attempts. We will also use this technique to create advanced in vitro models that we can use to detect toxicological endpoints. Thanks for listening.
All right, so I hope that gives you a visual of how our printer works, as you'll see a lot of printed objects in the results portion of this talk. So even though bioprinting is still in its infancy, there are clinical trial cases where bioprinting has been demonstrated to be successful. So as early as 2001, the young boy that is in the photograph here was one of 7 patients who were implanted with a bladder that was generated by seeding a bioprinted scaffold with the patient's own bladder cells. And you can see then the scaffold being grown with the cells here. And a follow-up article on this young man in 2018, or 17 years later, confirmed that he was healthy and he had graduated high school and college. More recently, bioprinting has been used to generate ear implants, and this has been clinically tested in 11 patients, including this young woman who underwent an ear reconstruction surgery. And so the advantage of using a bioprinted construct that involves the patient's own cells is that the expectation is a significant reduction in the chance of organ rejection after implantation. Another example is with artificial skin. So that's a bit of a misnomer. Artificial skin has been around since the 1980s, and it consists of a collagen scaffold, and it was found to accelerate wound healing. So lab-grown skin is still an active area of research. And there's a company, Poetis, who's exploring the automation of human skin manufacturing with bioprinting. And so the process involves taking a biopsy of the skin to be generated and expanded, where then the skin layers, the epidermis and the dermis, are separated so that the different skin cell types, such as keratinocytes and fibroblasts, can be isolated and expanded. And so these are all from the patient's own skin biopsy. These cells are then formulated into a bioink, which then would be bioprinted into the dermis and then epidermal layers of the skin. The skin would then mature by incubating at the air-liquid interface. And so in 28 days, then you will have a histological profile, such as shown here, that is representative of human skin, where you see the epidermal and the dermal layers as shown. And so this, this skin product, the POISkin, has been in clinical trials that started in 2022. And in those previous cases, the tissues were being bioprinted ex situ with a bioprinter that looks like some of the 3D printers you may have seen before. There are also reports of testing in situ bioprinting in the clinic. And so these images were recently published online in December, where the in situ bioprinter being made by a company called 3D Bioprinting Solutions was being tested in the clinic. So bioprinting is still, while it's an active area of research, it is moving closer and closer to the clinic. And so that's where, why aren't we seeing it yet more widely used in the clinic? And it's just these clinical trial cases that are being reported. And so while the bioprinting manufacturing process continues to advance in terms of the different bioinks that have been formulated for the various different types of tissues that we may want to construct, as well as all of the different bioprinting modalities that all have different advantages and disadvantages with respect to the geometries that can be created. We're still a ways away from recapitulating the complex microstructure as well as the biological function of an organ. And that's where, more research needs to be done to not only create those complex geometries, but also have that tissue-like complexity where there's vascularization, meaning the tissue has blood vessels, so that when it's implanted, it can be connected so that there's adequate nutrients that make it to the tissue, as well as innervation, so that there are nerves that can then help with communication between the body and the tissue that is implanted. So there's still much research to be done. Even at a basic level, you can think of bioprinting as a multi-objective optimization problem. And so we want to maximize printability while also maximizing biocompatibility. And in our research, these are the two variables that we focus on when looking at, are the prints being compromised or not. And so these variables depend on different, or are affected by different parameters. Some of those parameters are set by the application, the use case, or the users. And some of the parameters are dependent upon those set parameters, such as pressure is dependent upon the nozzle diameter and extrusion rate, and viscosity is dependent upon the concentration of the polymer and cells, as well as the shear rate of the bioink that is made. And so this is where there have been efforts to try to use different algorithms to better study bioprinting. And so those have been in, for example, the quality control space, where applying machine learning and image processing, the bioprinting process can be monitored. And using a metric called the extrusion multiplier, this particular group was following the flow of the bioink. And if the flow of the bioink was disrupted, where the flow depended upon the layer height as well as the nozzle diameter, both inner and outer nozzle diameters, so you could create a profile where you have boundaries of or the range where you expect the printer to operate, as well as an optimal line, then the deviations from the optimal line could then be automatically detected to either make a change, process change, or abandon the print, for example. So this is where quality control has applied machine learning approaches. My own group has also explored the application of machine learning to predict those two parameters I mentioned before, printability, via examining the filament diameter, as well as cell viability, looking at how many cells remain alive after the printing process. We collated a manually curated literature database with multiple different parameters to see if we could use machine learning to rank the importance of those different parameters in terms of these two outcomes, as well as to predict what the potential outcome would be for different suggested formulations that we were considering. And so then we found that for the random forest regression, there was actually fairly decent predictions of the final filament diameter that could result, as well as the cell viability that could result from applying these formulations with extrusion-based bioprinting. But these are, again, applying algorithms to the bioprinter under normal use cases. And so when I learned about Irfan Ahmed's research in the cybersecurity of 3D printers, it seemed like a great opportunity to collaborate and extend our research to look at the cybersecurity of bioprinters. And so our hypothesis going into this study is that bioprinters currently lack features that allow for security compromises to be detected and logged during their normal use. And this means that there is a need for safeguards to protect the bioprinters against cybersecurity threats, which may include sabotage attacks. And we were unaware at the time when we started this project of any available solutions to protect bioprinters from cybersecurity threats. So why would a bioprinter be attacked? What would be the motivation of an attack? There are several different goals that an attacker might be trying to achieve. Not shown on this slide include goals such as political or financial gain. But often it could be they want to do unauthorized printing, meaning that the printer is being used at the facility to print something with that it's not supposed to. It could be for surveillance. So the attacker may be wanting to steal information about either the printing process or the printing facility. It could be denial of service, or trying to stop the printing process or stop the network communication in the facility. Or it could be an integrity breach where the attacker is creating defects that could go undetected, either in the print object or the print environment, and that would impact the system. And so we focused on these integrity breach type attacks or sabotage attacks. So the bioprinter did not have sensors to detect changes in the system. So we had to first outfit the bioprinter with different types of sensors to collect what's called side channel data. And so this is where to understand if the HEPA filter in this bioprinter that maintains the sterile environment in the chamber during the bioprinting process, if that's being affected, a microphone was utilized to then detect any changes in the fan speed. I mentioned that the some of the bioink formulations involve UV cross-linking. And so that's where then a UV sensor was installed to collect data on whether the UV light was on or not. There's also two different UV lights installed, and so we could also detect if the light source has changed. We installed a rotary optical encoder assembly to collect the positional information of the bioprinter, as well as a thermistor or a thermal resistor to collect the temperature data to see if the temperature controlled extruders were affected as well. And so this is a summary, I know it's quite busy, of the BioSafe framework, which is the cybersecurity solution that we're proposing for the bioprinting, extrusion-based bioprinting, such as the printer shown here. And so how this BioSafe framework works is that we have the ground truth G code, so the instructions that are intended to be used for creating the bioprinted tissue. But then we also, with the sensors that I showed you on the previous slide, can collect side channel data where we monitor the position, temperature, UV, as well as HEPA filter fan speed. And so we have all of this data to then kind of compare and see if the process is running as expected. And so both of these data sources are then processed and represented in both the time and the space domains, so that then they can be cross-compared and analyzed to see if these different outcomes, so the UV profile, timing of the printing, the position or the height of the extruder, the temperature that was set, whether the HEPA filter is active or not, as well as the geometry of the print, all of these are proceeding as expected, or if there is an anomaly that is present. And so if an anomaly is present, then the system would generate an alert that then could be acted upon by the user. And so we looked at, there's 7 different attack types for further investigation. And this table here shows you the 7 attack types, as well as the magnitude of the attack that can be detected by the system, how fast the system can respond, as well as then the type of alert that is provided by the system. And so of these 7 different attack types, we focused on the first 5, as we found in the preliminary investigations that the print object that we chose for examining these different attacks involved a short print time, in which case the UV illumination that would be provided would not be expected to damage the cells. And so that's where, and if we were also using a bioink that did not necessitate UV illumination. And so that's where then the system could be just tested as whether or not it can detect the light deviations or not. Same with the HEPA filter, where the print duration was so short that, testing for sterility changes would not make sense for this particular print object, because the time wouldn't allow for be able to see if there was any, say, contamination that was caused. So we're going to focus on the first 5 attacks, so nozzle switching, quick pause and print, layer thickness, print speed, and extrusion temperature. And so the metrics that we used for printability, there are multiple metrics that are proposed, and we even reviewed several of these. And so there's no standard yet in the bioprinting community as to a metric that defines printability. We chose to focus on the printability ratio, which is this metric boxed here, because we chose to use a simple square box as our printed object. And this way we can utilize the ratio where if it's a perfect square, then our value would be a PR of 1. And as the print quality and the printability deviates from ideal, then the PR value would be less than or greater than 1. And in addition to printability, I mentioned we also looked at cell viability, and you'll see primarily we looked at that with the temperature attack. All right, so here is an example of our normal printing process. In our experiments, we used a 2% agarose, 2% gelatin hydrogel with and without embedding of cells. And normally the color of the hydrogel may depend on the media that you use. And so you can purchase or make your cell culture media with or without indicator dyes, such as phenol red, which helps to detect the pH. And oftentimes they will be similar in color. And so one of the attacks that we looked at was nozzle switching, where the extruder in a multi-extruder bioprinter is changed when it's not supposed to. And so to help visualize this attack, we had both the clear bioink as well as a red dyed bioink, and perform the prints when the attack was present. And so you can see, as compared to the normal printing process, when nozzle switching occurs, you can then, at least in our test case here, you would be able to see the change in the source of the ink. And so that's where this is for demonstration. I'm showing you here the different photos. However, in a real process, this is where this could be a undetectable attack, in the sense that if you were watching the process, if you didn't notice that the nozzles, the extruders had changed, then if both inks had the same, say, color, whether it be clear like this or pink like this one, then it would be indistinguishable, and yet you are switching the cell types. So to give kind of a more concrete example, if we were building that human skin, like I showed in the one example where, say, this nozzle had the keratinocytes and this nozzle had the fibroblasts, then you may want to put down, say, the fibroblasts first and the keratinocytes second. But if you switch the nozzles, then the cells are placed in the opposite positions, which will affect then the tissue and its functionality. Another attack we looked at is what we call a quick pause in print, where the extrusion of the bioink is stopped briefly, but the extruder still continues along the print profile. And so this can lead to small defects in the print, as you can see in this example, where it was printing the square, but you have this gap shown here. Another attack that we looked at was the layer thickness, which relates to the height of the extruder from the last layer of the printed material. So I had mentioned that we printed square boxes, as you see here, and they were both either one layer or a 3-layer box. And so when you're looking at multi-layer or even with one layer, the layer thickness tells the height of the extruder. And so if you change that height, we went from 0.01 millimeters to up to 1.5 millimeters in height, then it can affect the print quality of your construct. And here I am showing you those printability ratio values, where as the layer height or layer thickness increased, our printability decreased. We also looked at print speed. And so this is where I'm showing you we're increasing the print speed from the speed that we had normally used in our prints to a speed that's about 2 times higher or faster than what we normally use to see how it affects the printed constructs. And surprisingly, by speeding up a little bit, we got slightly better PR values. However, as we continue to increase the print speed, then you could see that the printability decreased in some cases due to incomplete constructs could not be quantified. And so this is where the print speed also was found to affect the print quality. And then we also looked at extrusion temperature. And so here we started with the 37 degrees Celsius, which is the temperature that you would want to keep your human cells at. This is normal body temperature. And we increased the extruder temperature by 3 degrees Celsius up to the maximum temperature that the extruder can hold, which is 60 degrees Celsius. And you can see that the printability of the constructs degrades as the temperature increases. And this is primarily due to the fact that we are using thermally cross-linking hydrogels, such I mentioned the agarose and the gelatin that's being used. And as you increase the temperature, even for a short print, the temperature attack is noticeable in the cell viability. So here I'm showing you the normal printing process in blue, the cell viability on the day that it was printed, as well as 1 day after. And then in the attack prints, the cell viability on the day it was printed, as well as 1 day after. And so even on the day it was printed, you can see a slight decrease in the cell viability due to being held at that higher temperature, and it's more drastic the day after, where you see a significantly lower cell viability in the attack print. And so creating cybersecurity solutions for 3D printers has, there's several that have been proposed in the literature. However, they're looking at the polymer extrusion for say fused filament fabrication, 3D printing, or metal 3D printing. So in our case, we are looking at bioprinting, where then the bioink, where the cells are encapsulated in a hydrogel, is being used as the printed material. In addition, if we compare our solution and the types of attacks that it can detect, it detects 9 different attacks, whereas the closest to this is this solution here that has 6 different attacks that can be detected. And this is actually a solution that was also developed in the med lab here at VCU. And so again, the contribution is extending the different types of printing parameters that can be detected if they are altered, as well as the type of printing that is being protected. And so this is important if you think about, if some of you may be aware that the Central Virginia node has different test beds. And so one test bed is the medical device security test bed. And I had the opportunity to have a brief tour, and it was interesting to learn that, you know, a lot of medical devices, because they were developed before we were thinking actively about cybersecurity, that it's hard to retrofit these devices and make them secure in our new digital landscape. And so then as we are developing the bioprinting approach, I look forward to perhaps a bioprinter being included in this test bed, but we should be actively thinking about the security of the device as it moves from the bench closer to the clinic. And I think that this is going to accelerate because there is a strong emphasis for innovation in biomanufacturing. It's become a national priority, and this is where then we need cybersecurity solutions to safeguard these different biomanufacturing processes, which includes bioprinting, like I showed you here today. And it will be critical to securing these processes will be critical to ensuring that the products and are safe, as well as the patients and the consumers that are benefiting from these products are safe as well. And so I would like to acknowledge the students, the wonderful students in my lab, as well as the wonderful students in my collaborators lab who helped with generating all of this data that I had presented to you today. I'd especially like to recognize Eunice, Kate, and Barry, who performed the bioprinting validation experiments that I had shown you. And I am again thankful to the CCI Central Virginia node for sponsoring this study. And thank you for your attention, and I'm happy to take any questions.
Where do you expect to focus next?
So this is where we want to move beyond the simple square construct to more tissue-like constructs. This will allow us to investigate more time-dependent issues, as well as more subvert attacks, right? So I showed you, for example, that quick pause and print with the simple square box. It was easy to see the gap. Now, if you have a multi-layer large construct, it may be harder to detect some of those. So from a, I guess I see it from the bioprinting perspective, the system should already be able to detect that anyways, due to the sensors as well as the ground truth G-code being available. So this is again where there are other bioprinting modalities that we could also explore as well, either going from the extrusion printing to, say, one of those light-based printing approaches, or even to extrusion printing, but in different use cases where ancillary equipment is used as well.
All right. Thank you so much for taking the time out to do this. We really appreciate it. Thank you everyone for participating and coming out to be at this talk. Our next talk is next Wednesday at 10 a.m. and it's with Carl Elk. So I'm going to drop the registration link for that in the chat. Thank you all so much for coming. We really appreciate it.
Thank you for coming.